Hola, Cari.
Hola, ¿cómo estás?
Bien, ¿y tú cómo estás?
Bien. Acá no sé si se escucha, pero están trabajando mucho en la construcción del frente.
Oh,
Y
qué lata.
las máquinas suenan y como que se me mueve el piso todo.
Sí, o sea, no se escucha ruido, se escucha como una vibración nomás. Ay, ahora no te escucho. No sé qué pasa ahí.
Aló, aló, aló.
Mm, ahí sí, ahí sí.
Sí, no, está muy fuerte el sonido.
De más, de más. ¿Ya han estado? ¿Hace cuánto están ahí?
Hoy están construyendo como hace un año y tanto, un año y medio quizás.
Ah, bueno, sí, pues sí me contaste.
Sí, pero
Estaba
han
medio en
estado todo
eso.
el día súper bulliciosos.
Oh, me imagino. Sí, súper incómodo eso, las construcciones,
Sí.
mucho ruido. ¿Y te cuesta estudiar en general? ¿Como por eso?
Sí, pues, o sea, igual, o sea, igual me acostumbré, como que ya, como que me pongo el audífono y chao, pero cuando ocupan, no sé qué máquina estarán utilizando, que vibra mucho, entonces como que se mueve el piso y es como súper incómodo, como,
Ah, qué fue.
pero nada, nada que hacer.
Nada que hacer. Hoy estoy contentito.
Sí, yo igual estoy como muy cansada, como me gustaría tener menos responsabilidad.
Y sí,
Al rato lo
igual,
va a profe. Yo diciendo que quiero menos responsabilidad.
sí, igual sentía que partió como tranquila la semana, o sea, no me, no me he estado haciendo tanta cosa de la U, pero se siente que va de a poco tomando vuelo, así que hay que empezar a estudiar nomás.
Sí. Y yo estoy con la
¿Ah?
bebé. Entonces, o sea, no es FECMA, pero lo vi que te conté que estaba con etóloga.
¿Sí?
Pasa que le salieron unos exámenes muy malos. Y pasa que tiene como ansiedad generalizada. Pero creo que nació así. El punto es que. Ah, yo, profe. Pero la cosa es que estaba como súper enferma y tenía que ir a comprarle varios remedios como para como, como empezar el tratamiento.
¿Qué era lo que dijiste que tenía? Perdón.
Ansiedad generalizada.
Ah,
Llegó el profe. Hola, profe.
sí. Hola, profesor.
Hola,
¿Qué tal?
¿hace frío?
Sí,
Lo tiene té.
¿Cómo, cómo?
café para el frío.
Ah, café para el frío, sí, sí. No puede faltar.
Sí. Ah, there's noise now. Okay. Yeah, no, before we start, I think Macarena was the only person who came to the colloquia, which was kind of chaotically announced. But hopefully, the things that you've learned in the class were useful to understand what the hell Jason was talking about.
Yeah.
Okay, good.
It actually helped a lot. I could recognize some terms and I was like, hey, I know. I know what he's talking. Either way, I was lost in some part, but it helped.
Yeah, well, I mean, I think, he's talking about the polarization and the maximum polarization you can see and
Yeah.
the effects that tend to diminish or depolarize things, right? We had kind of talked a little bit about that in class. So hopefully your knowledge in the class makes things a little bit more approachable. That's kind of the point. The other thing, of course, was we were talking about today in Astro PH, the gamma ray spectrum, sort of generically in our galaxy, and that that will make more sense, I think, after the next couple of lectures, because we'll start to see how that's. I mean, well, this lecture we're going to talk about the spectrum of inverse Compton, And so the spectra that you see at those high energies are generally a direct result of the processes that we're talking about now. And then there's an absorption term that will come in when we start to talk about annihilation and pair production. So hopefully I will arm you guys with the knowledge to make sense of the chaotic world of high energy physics. Okay, any questions, doubts, thoughts?
I have a question. I don't know if you mentioned this last class, but how should I calculate my grade given the points of the homeworks?
So, yeah, I mean, unfortunately, well, yeah, on the homeworks, basically every homework is, out of some score, and you can change that to 100. And then you could change that to a Chilean grade by saying multiply by 6 and then add 1.
Okay, that is the base point.
Yeah.
Okay.
Yeah. So I think for like something like a 22 out of 26, it should be, I think it should be around 6. I think that's what it is. I did a spot check of Priscilla's grades. In some cases, it was a little bit difficult I had to read a couple of times to figure out what she was taking off. And she was maybe slightly harsh in some cases. And I understand where she's going with it, but there maybe could be some debate. I think I gave, well, in one case, I think in Juan's homework, she missed adding 3 points from one of the things he got right. So I had to fix that. I think in the case of Macarena and Karina, I gave you an extra point. Because I thought she, so I entered the grades into the system, into Canvas, so you can see the grades. And in there, I gave you an extra point compared to what she put, because I thought she took off a little bit too much on one of the things. Anyway, that's all things we can debate at some level. I'm still waiting for her to put more grades in. And I've been pushing and pushing. I just don't know where to go other than to start doing it myself. So yeah, so that's my internal debate. Regarding the exam, one area where many of you struggled was in problem 4. And so maybe let me open that and let's see. Stuck it. And just, I want to discuss it slightly. What? Dropbox. Okay. Screen. Okay, so you guys can see now. So problem 3, here we are. Oops, too far. Okay, so it was pushing you guys to kind of use what you would know, right? And so all you saw was this, and this. Maybe it would be easier to go back to the original exam too. Where the hell is that? Somewhere. There we go. You can see what you guys saw. Okay, so we had this. Come on. Very slow. All right. So we have this, and I gave you a bunch of wavelengths and frequencies. Obviously, you know the answers now, so it's a little bit hard to go back. I even gave you, this versus this is the white dwarf, this is the planetary nebula, and so, this ended up being free. Why would it not be synchrotron?
maybe the first thing we could say is because of its shape. Like the free one has a really distinctive shape, like with this, I don't know how to say it.
Well, it's flat, and then
Yeah,
it
this
bends.
flat
But I
part.
mean, you can have synchrotron that is flat too from, say, radio jets, right? So I mean, the synchrotron spectrum is just a derivative of the electron input spectrum, right? And so you could have some situation where you had an electron spectrum which was giving rise to that, right? But you would essentially need, so if this was S equals 0, then that would give you a certain P, right? And so you would have a power law distribution of electrons. Now, does that make sense? What's going on here? What is happening in the planetary nebula physically? The star, when it evolves, it sheds material on it's very slow, right? So it's going out at like 10 to 100 kilometers a second. And then the white dwarf control, the other part of the star contracts and becomes hotter, right? And so you have UV radiation that's ionizing. So it's taking apart the hydrogen atoms into protons and electrons. What are the typical speeds that you might expect here? And what is the distribution of electrons that you might expect? Is it going to be a power law, or is it going to be a thermal distribution? And that's the critical thing you have to ask is that, do I have the relativistic electrons from this in order to make this synchrotron? Right? And in this case, it doesn't necessarily make sense given the production, how you're producing the electrons, right? And you have a group of hot electrons, and of course, the Coulomb interaction is there, right? So it makes more sense that seeing this this relatively flat, not something steep, it makes some sense. And then of course you have the absorption, and honestly, you're not going to be able to tell if it's an absorption of -2 or -2.5. So that's unless you measure it really, really well, you're not gonna, it's gonna be ambiguous whether it's synchrotron self-absorption or self-absorption from bremsstrahlung. So you really have to think about the situation that you have, and do you have the ingredients to make synchrotron, right? And so likewise, we could come here and say, oh, we have this interesting thing. We're not really sure what the hell it is. Okay, this, we can say this is free emission, right? And this, we can say, well, this is the white dwarf, which should, I mean, the white dwarf should be hot, so it should be giving off a thermal black body-like spectrum, right? Although this isn't exactly a black body spectrum. This is curved, more curved, right? This is not r to the -2. So you could have some doubts, but I also told you that there's high extinction here, and the extinction is going to affect the blue more than the red, right? So these are going to drop down more than this. So it originally was more like a black body, but we didn't measure the peak, right? We don't see the turnover, right? And if you calculate where the optical band is, this is the optical band. And of course, a white dwarf is hot, so it's going to peak in the UV. So you're not seeing the peak, right? You don't know the temperature of it. And so this axis is super useful because it gives you an idea of what the energies are going to be like. So coming back, okay, this is a black body and this is free. So what the hell is this, right? Could it be a synchrotron? And you guys are all muted, but what did we already say about this? If this isn't synchrotron, is this going to be synchrotron? What would you need? You need even faster electrons, right? And you need them to be super compact because you have basically the synchrotron spectrum, which is, well, I mean, you don't even really see it, right? Because you've got some exponential fall off here, and then maybe you have a little bit of stuff here, and then you have the self-absorption. So that thing has to be ridiculously compact. And so what is the likelihood that you're going to, this is in the infrared now. So what conditions would you need in terms of magnetic field, in terms of the electron speed, in terms of the density to see that, right? So you have all the tools, and it's just a matter of going through and applying a checklist and saying, okay, does this situation have this or not?
Professor, and what is the reason we see like this difference? And I don't know that we only, I don't know, we don't have only free and then the black body. Why do we have like this change? What is
why is
process?
There this?
Yeah.
Well, that's the trick, right? Is that, okay, what the hell is this? This is the star, this is the free, and what do you know about things that emit something that looks kind of like a black body at roughly 100 micron?
I don't know if I can answer this because I got it wrong, but so I let someone else.
So you have something which, if you were to consider this a black body, what is the temperature of the black body?
It's the order of 10 Kelvin? Or
100 Kelvin.
Or 100, yes.
So, I mean, the CMB is 3 Kelvin, so that's peaking in the millimeter, right? So millimeter, this is centimeter, millimeters right here. So CMB is peaking here at 3. So, yeah, actually, it's like 30 kV. Sorry, 30 Kelvin is the peak here. And so what type of material emits at 30 Kelvin?
Dust.
There's dust everywhere, right?
Yeah.
And so, I mean, it just so happens that you have that, you just evacuated the outskirts of a star, and okay, you're ionizing some portion, but apparently you're not ionizing the whole thing, and somehow dust is formed. And it's not super intuitive, right? Because this is an ionized region, and so what it implies, the fact that you see this there, is that there's clumpiness, right? And admittedly, it's not the easiest thing to envision of how you get both of those things together. But physically, that's what's happening, right? I just stole this from Ned, and I had to fill in some of these points because they're not fully measured. But there are a few points here, there are a few points here, there are a few points here. So I filled them in to make it clearer what's going on. But this is a source that exists. And so, just taking something in nature and saying, okay, this is, how do we figure out what the hell's going on, right? And trying to give you the clues that these are all things that you've seen before. I think I said that somewhere, right? So that there are only 3 possibilities. It's a black body, it's free, or Armstrong, or it's synchrotron. And just remembering the ingredients you need to make those, right? You can exclude things. Okay.
I have a doubt. In the same part of the spectra. So if the dust is emitting, so we see an increasing part in the curve and then a decreasing, and the second part is because the dust emit and also absorb.
Well, the dust is a certain temperature, right? So it has a certain velocity, and then remember that, effectively what happens with the black body, the Planck law, is that you have some velocity, and then you're not going to be able to generate any light at higher frequencies because you have a photon discreteness due to the velocity, right? And this is the case. This is why you have exponential everywhere. At some point, you just no longer have the energy input from whatever's making the light to give, right? And so it's just a very common feature that you have these exponential curves. Yeah, okay. So hopefully this is a little bit clearer. And some of you got the right answer, so it was apparently doable. Okay, so where the hell are we now? We have been talking about Compton scattering and inverse Compton scattering. And we had talked about the single scatter in terms of the energy requirements, right? And so the idea now is to look at the spectrum of this. So we had done this before, and we talked about certain situations: front reflection, back reflection, beaming. We had looked at sort of what the energy limits were, and remember, where the hell was it? Sort of starting here, right? We had basically the electron would be able to give sort of gamma squared to upscatter the photon, as long as the photon had much lower energy than the electron. Okay, so the average energy is going to be sort of a 4 gamma squared, but there's a strong tendency for the backscattering, for instance, to just be downscattered, and for the front reflection to be upscattered. So we went through and looked at how this would look for a distribution of photons for a single scatter. Right, and so we did this and mainly had the energy requirements that we needed to demonstrate, for instance, whether an electron would lose energy via synchrotron radiation or via an inverse Compton. And yeah, then we looked at the sort of power distribution, so the total amount of energy that's coming out. And so now we want to look at this as a function of frequency. Okay, so without further ado, get that. And by the way, for the question, yeah, the classes are automatically recorded, but then for some stupid reason, Zoom had introduced a setting where it deleted after a day. And so I could recover them, and I recovered them. So they're back sort of, but they after a month, they delete automatically. And so the first several lectures are gone because they weren't saved. But I have the other ones. Okay, so we're going to do look at how this interaction, or how the upscatter works as a function of frequency. And so this inverse Compton spectrum is going to depend very strongly on both the incident spectrum, right, and the distribution of electrons. And you're going to have an intimate relation between these two because of the fact that as the photon gets close in energy to the electron speed, right, or the gamma of the electron, you're going to not be, you're going to drop out. And so you have to sort of piecewise integrate over the electron distribution for the given spectrum, right? And each of those sections is going to contribute something to the overall spectrum. And this is again for a single scattering. So you have a population of photons, you have a population of electrons, and every electron in here is just going to scatter a photon once, right? So the tau here is very, very low. You just get a single scattering and the photon leaves. That's what's meant by a single scattering. Okay, so the general spectrum here, what we can do, and sort of the benefit of this, is that we only really need to assess some energy E versus a given electron energy. And we can get out the resulting spectrum based on that. And this is because the general spectrum is going to be found by averaging over both of the distributions. And so this allows some flexibility there. And so we can rewrite things or talk about things in terms of an intensity and the emissivity, J, right? We can use these terms in terms of the number of photons rather than their energy. So we can talk about the number of photons, not so much the energy of the photon, to sort of simplify things a little bit. Since we need a number of photons interacting with a number of electrons. Here we're going to assume isotropic distributions to start, to make things simpler. And we're going to assume that Thomson scattering holds within the electron regime, right, in the electron's frame of reference. And so we have some incident energy, which we can rewrite as this, as some number of incident photons over some very tiny width of energy. And so this is the number of incident photons per unit area, per unit time, per sterility. And so in the K prime frame, when we transform this, we're going to transform it and we're going to have our number. And then we're going to have this energy difference here. And then we have this delta function. So this is the sort of important factor here. And so we can then take this thing and we can split this out into, rather than energies, we can talk about what this would actually look like. And so we can take this and we transform it into the E prime frame. And so we have something which looks like that. And so then we can go again and we can say, okay, we can rewrite this thing as taking the cosine prime as U here, and we can play tricks with the U du to kind of do the derivative of the angle as well. And so now we can then think about the emissivity in the K prime frame, right? And so the emissivity here will be this thing. This is the emissivity of the upscattered photons now, right? So they've interacted with the electron, and this is now the distribution of photons coming out. And that's going to be proportional to some number times the Thomson cross-section, and then integrating over this input spectrum, or the input intensity, the number of photons. So that would be our output emissivity or emission function. And we can integrate over all angles, but since we've made this substitution, we're now integrating between -1 and +1, rather than between -180 and 180, 0 and 360. Okay, and so this thing is the number of photons in some volume per unit frequency per unit sterility. And we're assuming here elastic scattering in the K prime frame, which is why we have this Thomson scattering cross-section. And so in total, so if we come back here and we do this integral, and we had this thing here, what we end up getting is sort of these things. We get the energy here, and this is then divided by our velocity, our gamma, and our initial energy squared. So this thing holds for a very small range. And we initially had a E minus E prime, and when we go through the process of transforming it to the electron frame, interacting, and then transforming it back out, this range has changed by the scattering, right? So it's become a little bit larger on each side because there's the downscatter and the upscatter. And so this is why we end up having, this is appropriate only between this regime of energies. And so we have the lower energy range and the upper energy range, and this energy is in between it. And outside of that range, this is 0, right? And then we step through and we do delta functions for the entire spectrum and step through and do this process piecewise, right? And this is what is sort of meant by we can do this in an average sort of way. Does this make sense? Okay. So this is the emissivity in the electron frame. We still need to transform it back to the K frame. And so we want to find the emissivity there for this energy. And so this energy, of course, has this frequency, right? Because that's ultimately we want the frequency dependence of this. So this is now the emissivity in the J prime frame, and it's related to this. And then we have simply an extra factor here, which is this transformation of this energy. And so plugging in what we had here, we plug that in, and we can end up, these things cross out, and this E prime comes over here. So it is a relatively straightforward transformation. The only factor, the extra factor here that we have is this extra gamma. And so we can kind of think of this as, you know, if we had this emissivity, basically the number densities would transform kind of in this way, which is a little bit odd to think about, that you would have numbers that would increase. But in effect, this is sort of what ends up happening. So again, this is only going to hold. So when we transform this back, we have an extra factor here, which is the gamma, and then this 1 minus B mu1. And so now the energies have increased a little bit more with this extra transformation back. Okay, so again, this is for just within this range, and then it's 0 otherwise. And so if we have an isotropic distribution of electrons, and we want to average over the angles that we see, so averaging over this U, what we end up having is an emissivity, which is now, we're averaging over this thing. So we take the integral of this, and that will be more or less these constants here, which move out. And then we have, depending on whether it's front scattered or back scattered, right, how the photons are coming in with respect to the electron, we will have certain terms that come in. And so if it's down scattered, so if we ended up in, you know, in our angle, where was it? Here, yeah. So, right, if we had the backscattering solution, then we'll end up sort of downplaying. If we have front scattering, we'll end up sort of upscattering it. And so coming back here, we have the downscattering regime, which holds between, if the output energy divided by the input energy is less than 1, right? So the output energy is downscattered, so the energy decreases. And that goes between the range 1 minus beta to 1 plus beta up to 1. Then we have an upscattering regime, which is if the energy is higher than the input energy, up to some upper limit, which is 1 plus beta divided by 1 minus beta. Remember, if beta is close to 1, then this is a pretty large number, right? And if beta is close to 1, this is a pretty low number. Right? And so the difference here ends up being, whether it's downscattered, then we have this proportionality or this factor, which is, it comes in here. And so this is the energy range here times this factor minus this, which in the extreme relativistic case is close to 0. And then if it's upscattered, we have this case, which is, this thing is close to 2, and then this thing might be pretty high, but this thing is very, very low. And so this may wash out, but this is sort of a relatively, you know, it's some factor that is upscattered. So you get a difference here depending on the orientations of this. And so the output emissivity is directionally dependent, right? Which is what we had mentioned before. But since we're averaging over different electrons, which are going in a random distribution, we're still seeing the emissivity go in all directions, but it's downplaying a certain fraction of the photons and upscattering, downscattering a certain fraction, upscattering a certain fraction. Are you guys following me still? Okay. And then, of course, outside of these energy ranges, it's 0 again, right? So we're still just in this little section of energy. Okay, so what does this sort of look like? Again, we have, I can show, we have this initial frame, we have an initial electron, and now we have electrons which are oriented wherever. So for each individual electron, we transform, we have a photon distribution which is now directionally dependent. We do the Thomson scatter, we have the output probability, we transform the output probability, and we have, again, directionality. But now we're having electrons in all the sort of distributions, so this is happening in an isotropic fashion again. But the spectrum is going to change, right? Depending on gamma. Okay, so we can do a couple of cross-checks here. One cross-check is we want to have a conservation in the number of photons that are basically the number of photons per scatter. And so if we integrate this thing, we should end up with the input number times the Thomson cross-section, which is the number of scatters that happened in the electron frame. Right, so this should hold. Another one is to estimate the average increase in photon energy per scatter. And so that would be taking this output distribution of photons and looking at the change in energy of each of them and integrating between 0 and infinity for all the energies. And that integral should be equal to the number times how many were scattered, then the average boost in energy, which is going to be gamma squared, the initial energy, beta squared here, but if it's ultra relativistic, this is 1, and then 4/3 because we're averaging over all angles. And then the original normalization, right? So basically it's just this average energy of increase, the number times the number that are scattered and the original. So these double checks should hold in this case. If we have a very sort of ultra relativistic case, so beta is roughly equal to 1, then what happens is that the emission function back here, oops, this term dominates in the ultra relativistic regime. This term is downplayed, and of course this is 0, so this thing is where most of the energy comes out. So we get an upscattering in this isotropic approximation, and so we can approximate this outgoing emissivity as this. And so we have most of the factors here that we had before, and we have this extra function. And this function is basically can be approximated as this, where x here is this ratio of energies divided by 4 gamma squared, which you then see here as sort of as well. And this will apply between a range of 0 and 1, which is this is the maximum energy that can be given. This is 0, right? So this is the minimum amount that can happen. And again, this should hold for this case within this limited energy range. And we could also, this is the angle averaged version of this. If we had an exact angular dependence, then this functional form would have this sort of relation. And so this is an approximation. This is sort of a slightly more exact form. And so this is all very tricky to visualize. So this is a little bit easier way of seeing it. So this is the initial energy, and this is the output energy. And so when gamma, these are for different gammas, right? So when gamma equals 0.1, there's not much energy in the electrons, and so there's not much change. It broadens the distribution a little bit, but not much else happens. As you go to higher and higher gamma, you see that the upscatter becomes larger than the downscatter, right? The number of upscatters, or this is actually the sort of amount of energy that comes out, is higher in the upscatter versus the downscatter. Right? So this is just the output emissivity normalized by a couple of factors here. The input energy, the Thomson scatter, the number and the number of scatters, and the overall normalization of input photons. For this F form, this is again between 0 and 1. This is our value of X here, and this is the approximation, and this is the more exact solution. So you can see the approximation does pretty well, except at very, very low X here. And that's what these two things are showing. Okay, so the overall result here is that you get an upscatter, and the sort of energy dependence of this kind of ends up looking like this in these terms. Okay, so that is for a very specific situation and over a very small energy range. And so now what we can do is extend this to some arbitrary photon spectrum, right? So we only had a sort of small spike energies before, and now we can extend it to whatever spectrum we want. The only critical assumption that we're going to make is that that photon field is still isotropic, right? Because that simplifies a lot of things. And so this photon spectrum will have frequency dependence, which will look like this. So the frequency dependence will just be sort of proportional to this intensity here as a function of energy. So basically this is going to have a range of energies, but again, between this small range, and we can shift it, but we will sort of use this arbitrary spectrum coming in. And so now it has some frequency dependence. That's the key thing we're talking about. And basically we're going to say that this is just over a small range in energies. And so it vanishes for very small or very large energies, and it has some maximum, which is basically at the average energy. And we're going to assume a power law distribution of electrons now, rather than a thermal distribution. And so here we could have a power law distribution which looks like this. We have seen this before, right? And then what we want to know is the total scattered energy per unit time, per unit volume, per unit energy. And so that thing here, this is the output energy that we get after the inverse Compton scattering. That's simply going to be the distribution of the emissivity, or the emission function that comes out of the scatter, right? So this is just J for E1, this is the final energy. And because we're looking at the total scattered energy, it's this photon field times the energy that came out, right? And then 4 pi just to average over the entire volume. So that thing here can be broken down into a couple of integrals. And so we want to integrate over the energy distribution for the photons, and we want to integrate over the velocity distribution for the electrons. And so in doing that, basically this output here will be a function of our input spectrum over whatever energy range we have. But once we transform it, we have this extra factor here of E1 divided by E. And then we need to integrate over our electron distribution. And that means integrating over this functional form. However, in order to sort of do this integral, we also have to integrate over this functional form here. Oops, I went too far. Come on, there we go. This thing, this F here, right, which depends on gamma, right? So we need to integrate over that, and it also has an energy dependence. So we need to keep it here as well. We need to integrate this thing over this as well. So we can change variables here. And so we can change from this thing to this x, which is what we did before, right? So this is just x. And then this will change this to some x's and move the energies out here. And so by changing variables, we have this thing into something which looks like this here. So it has this functional form x, and then rather than this, we now have this, but we need to transform or move the energy here. And so we have a p to the minus 1 divided by 2 here. We also had another energy here. So this was, I think that all works out. Yeah, because there's an extra factor here as well. So we have to integrate over this thing, we have to integrate over this thing, and then we have our E1, which came from here, which we pull out, and this has a slope dependence now. We have an extra couple of normalizations, and then we have a cross section as we did before. So this is all very rapidly going through this, but just to sort of demonstrate kind of how you would do this. So if we assume here we have a limited range of E over a limited range of gamma, we can simplify this, and I put that in quotes because it's a pretty terrible integral to do. And so we end up having that this thing now sort of becomes this, where we now have a function here, which is grabbing all of the different slope dependencies which come about into one factor. And then we have an energy dependence, which is the same here as this. And we have an integral over this thing. So we've basically integrated this thing, and that's resulted in this, right? And so then we have an integral over this thing. And so this is not too bad to do. And so we can do that integral depending on what this functional form is. And we're calling that this is only going to be valid over a certain range of energies. And so the output of this, and this is, be careful, this is the functional, this is actually the flux in terms of x, and this x is not this x here, but it's a normalized version of the energy or the frequency. I stole this plot from somewhere else. And this is just the ratio of this frequency. So the input energy divided by the initial energy, and then the flux coming out as a function of the output energy. And so what you sort of have going here is, if you had a gamma of a very low gamma, then you would spread this out a little bit, but nothing would really change. The energies wouldn't change. As you increase gamma, you end up getting forward scattering dominated and downplay the backscatter. And so you end up with a forward scattering, which this peak, this average energy ends up being roughly 2 times gamma squared in terms of this ratio, right? So the peak will happen at 2 times gamma squared. So for 100, gamma of 100, this peak will happen at around 20,000, right? For 10, it will happen at around 200. And you have this spectrum that's coming out. You have a portion which is going as nu squared. You have a portion which is going as nu, and then you have a cutoff. And the cutoff is due to the fact that the electrons stop giving energies higher than a certain amount, right? So you can't boost the photon any faster or any higher than that. And so this is again for a very specific situation where we're taking a small range in energies but with an arbitrary frequency, and then we're taking an electron distribution over a range of gamma, and that is what will produce this particular spectrum. And so then we would need to integrate over a larger fraction of the spectrum and over a larger range in gamma, and we would have combinations of these things that would end up giving us a pseudo continuum. Does that make sense so far? It all ends up being a very complex process to you have to sort of forward model everything through to do. And so we can take a very specific example, and that's basically that we have an electron distribution with the power law, and then we have a photon distribution with a black body distribution, right? So now this functional form of frequency looks like this, right? Which is our familiar black body formula, and then we had a power law distribution of photons. This is maybe a natural situation if, for instance, you have a set of cosmic rays and you have the CMB, right? Or you have a stellar field or something like that. So then going back and integrating through each of these things, we would have the energy outcome as a function of the volume, as a function of time, as a function of energy. This would have this sort of functional form. And then this thing here would be this AP that we talked about before, and then we have a gamma function, and then we have a, I guess there's a run and zeta function as well. So it's non-trivial integrals to do here. But we end up having a dependence which actually has a power law shape again. And so this photon distribution will be upscattered by this, but will impart the spectrum from this electron distribution, right? So we no longer have a black body spectrum, which is interesting, yes. And so we could extend these results to various sort of problems, although doing these integrals is not trivial, right? And there are lots of sort of tedious details here. And we can also extend these results, to any sort of isotropic field and electron distribution. We can include Compton effects. We can include Klein-Nishini cross sections if we want, and tweak the details of everything. It gets much trickier when we talk about anisotropic seed distributions, photon seed distributions, because obviously the effect of the Compton scattering is very dependent on where the photons are coming from, right? And so you can get very nonlinear effects because of the anisotropy of these fields. And so one interesting case here is to think about an accretion disk, right? And so the accretion disk is the source of very hot, sort of material. It's temperatures of 10 to the 5, 10 to the 6, so it's emitting in the UV. So there's a huge radiation field coming up from that, and it has magnetic fields. And so you have a corona of hot electrons, which is sitting above it, right? And so you can imagine that those electrons, which are relativistic because of they're only being sort of accelerating innermost portion of the disk, and so they have speeds of tens to 100 of keV, and in terms of energy. And how is that cloud of electrons going to react to this photon distribution that's coming up from it, right? And so we can kind of think of this as the electrons are sitting in the center, and they're being surrounded by a hemisphere, right, a hemisphere of photons coming in. And so we have a situation which looks like this, right? The photons are coming in like a bowl, and we have the electrons sitting in the center. And the electrons, some of them are going up, some of them are going down, right? And of course, if they're going up and the photon field's coming from behind, it's mostly downscattered, right? If they're going down and the photons are coming in, then it's mostly upscattered. And so you get a huge differential in the inverse Compton sort of spectrum, or the power for electrons going up versus down. And you can calculate this as a power ratio, right? So the power ratio going down looks like this, the power ratio going up looks like this. And so we're just integrating over the differences in this angle theta, which we now have as a parameter du. And so if we do this integral and this integral, what we end up getting is for this one we get this, for this one we get this. And so this ratio of the power going down is 7 times higher on average than the power going up. And so you have this seed photons and they interact with this, and then you get a bunch of new photons, which are upscattered, right, to X-ray energies, which are irradiated back on the disk and can then interact with the disk. They can either reflect off of it or they can heat the disk further. So you get very interesting situations from these types of anisotropes. So, you know, what would happen? One question here is that, you know, if these are the electrons which are sitting pretty much at the disk. And so one model which people use is the so-called lamp post model, where the electrons could be sitting at some distance above the disk. And what would that do to this different, you know, this ratio here? If you move this electrons, if you move them up higher, what is this going to, how is this going to change this and this? No one knows?
Multiple scatterings?
Hmm?
Maybe it could be multiple scattering between the layers. The
Well,
question
what's going to happen to the distribution of incoming photons as you move the electrons up away from the disk? Right, they're initially sitting in here and they're getting irradiated from all sides. As you move it up, the photon distribution starts to collect more and be more anisotropic as well. And so what will that do to this ratio? Right, it should increase the ratio. And so depending on how high up they are, you might get a larger differential and a larger directionality towards the central portion of the disk. And so, you know, you can have very interesting interplays between the electrons and the seed photons depending on that. Imagine a jet, and you also have very interesting distributions of the synchrotron radiation, which is being generated in the jet, and the electrons, which are also in the jet, or it could be clumpy, right? And so you could have clumps of electrons which are then seeing a photon field around it, which is very directional in this direction or this direction. And so you could have, and they're also moving, right, with some velocity. And so they will likely not see the photons going in this direction, but all the photons coming back in this direction, they might interact with somehow, right? So you can get interesting effects because of this directionality. But you know, this is only, of course, in the super energetic, ridiculously, you know, relativistic processes. But those are the kind of processes which we were talking about at Astro PH today, right? You have a pulsar nebula, right, where you have hot electrons which are coming off of this thing, and they're interacting with the photons, and you know, if you looked at the Crab Nebula, it's like a torus and it has a jet. And so, you know, depending on the orientation, you might see very different things in terms of the gamma ray distribution coming off of that. Right, so just hopefully this puts it into perspective a little bit for you, and also puts in perspective how sort of stupidly difficult it is to try and model this, right? Because you really have to know what's going on, and you can have nonlinear effects that come into play. Okay, so that was again for a single scatter, and Laura touched on a point, which is we could have multiple scatters, right? And so if we have multiple scatters, you have an upscatter, and so now you have an energetic photon, and then it interacts with the electron field again. If if the density is high enough, right? If tau is relatively high, right? What is it? The mean path length isn't enough to leave the distribution of electrons. You get another upscatter, and so you could have multiple upscatters. And this process of multiple inverse Compton scatterings, while traveling through, say, a finite thermal material in the Thomson limit, like what's going to happen? You're going to get, you're going to be throwing all of these photons up to higher and higher energies, and you end up getting a pileup of photons sort of at one end of this distribution in terms of the spectrum that you end up getting. If the medium is finite, you have a certain number of scatterings, right? And so this whole process is called Comptonization. There's multiple scattering, and there's a term called the Comptonization parameter, Y, which describes how many inverse Compton scatterings there are, and when inverse Compton becomes important, and whether it will change the photon energy or not. And we can think of this Comptonization parameter as the optical depth, or it's akin to the optical depth for the inverse Compton effect. And so Y is basically just the average fractional energy gain per scatter, and then the number of mean scatterings. Right, so it's slightly different. The number of mean scatterings is kind of what tau is. And so this is the energy per scattering. And we can evaluate these things. So if Y is much greater than 1, what this means is that the photon energy and the spectrum will be very substantially altered. When it's very, very low, there's no change in the spectrum, right? And so we can evaluate this for a very simple distribution. So let's say we have a thermal distribution of electrons, and we're in the non-relativistic limit. So the amount of change is relatively small. And so here, our output E delta E divided by our total E, or this is our change in E, divided by our output energy, is going to be related to, or not output energy, so this is the input. So our change in the input energy in the electron frame versus the input energy is going to be just this, right? So this is the output energy, this is the input energy divided by the input energy, and roughly speaking, if we're in the non-relativistic limit, this will basically just turn into this. So it'll be a very small change relative to the energy of the electron. In a lab frame, when we convert this delta E divided by E will be equal to this here. So again, our rest energy, we have this extra term here, which is the efficiency with which we have scattering. And so it takes into account the temperature of the electrons divided by the rest energy of the electrons. So that's more or less the actual energy here. But there's this extra term alpha. And this extra term alpha is basically the efficiency with which a system can come into equilibrium via scattering alone. And so we can sort of estimate this and say, okay, let's say we have this interaction between photons and electrons, and the only interaction is between scattering. And so we want it to come into equilibrium. And so if the photon density here ends up being relatively small, we can neglect stimulated emission, which would be known as the non-degenerate limit. And so in this particular limit where the photon density is relatively small, we can estimate the photon distribution as a Bose-Einstein distribution. And this means that, we're not creating or destroying any photons in the process. And so we're just in a pure scattering regime. And so in this regime, the average energy of these photons is just simply the integral of the number times the energy per energy, and then divided by the integral of the number. And this should be on average 3 kT. If we took the average of the energy squared, this should be 12 kT squared. And so we can think about the average delta E. The average delta E in equilibrium should be 0, because the scattering, basically you've now you're going to upscatter as much as you downscatter. And so for this thing to be 0, right, coming back to this equation and taking it, basically multiplying E on this side, right, or multiplying E on this side, and then taking the average of this. We have these things pop out. We have the average E here, and then we have the average E squared here. So we can plug in 3 KT here, we can plug in 12 KT squared here, and we have this equation, which simplifies to this. So if the thing was in equilibrium, we would need an alpha factor of 4 for there to be no net energy difference, right? And so in the non-relativistic limit, basically we can plug in our factor alpha here as 4. And so in the non-relativistic limit, we come back to this, we multiply this on both sides, we put in our alpha, and we have this as our non-relativistic limit. And our relativistic limit, we originally had from long ago, that we have a photon, we go into the electron frame, we scatter it, we gain a factor of gamma, we transform it back out, we gain another factor of gamma. And so the input versus the output is different by a factor of gamma squared, right? And so the delta energy change in the relativistic limit is gamma squared E, and then times 4/3 because we're averaging over these angles. And so in the relativistic limit, we would then have, we can sort of frame this in terms of what is the average gamma squared here, and that is going to be equal to this. We can plug in what we had here, and we end up with something which looks like this. And so this average is going to be roughly equal to this. So we can compare the non-relativistic limit versus the relativistic limit. And for the most part, this would, this will be a strong boost because we have this factor here of KT divided by MC squared. Okay. So why is this important at all? And so we can think about this. This gives the average energy that is per scattering, right? So we in the non-relativistic regime, we have some factor here. In the relativistic regime, we have some factor. And then we want to know what's the mean number of scatterings. And so to work out the second term here, the mean number of scatterings, this is going to be a maximum. Sorry, we have someone working here downstairs from us. We have a maximum between tau and tau squared, right? So this is kind of similar to the random walk problem we discussed before. Here, tau is going to be proportional to the size of our region, some factor here, which is the electron scattering opacity, and then the density of electrons. And so this thing is just the Thomson scatter divided by the mass of this proton, or it could have a wavelength dependence as well. And so our Y factor in the non-relativistic regime is just this times this, and in the relativistic regime is just this times this. And we would have to estimate what this was depending on this, right? Whether we're in the optically thick regime or the optically thin regime. And so repeated scatterings here, say off of a thermal medium of non-relativistic electrons, would result in a final energy which was proportional to the initial energy times e to the y. And so we would, this is this Comptonization parameter, provided that this final energy is less than the energy of the system, right? Less than the energy that we have here. After this case, the final energy can never be above this. And so we have a cutoff, which is again, sort of related to our full-time quantified quantization. Sorry, photon discreteness, that's what I mean. Okay, so this sort of factor here, as it can have a frequency dependence as well. But you generally will have a sort of boost which will come like this. And so if y is greater than 1, right, you will have a pretty strong upscattering. And because you have multiple scatterings, and so you get a substantial boost to it. We can rewrite this. So typically, if we have what we found from our initial sort of exercise where we had a power law distribution of electrons and a photon field, basically what happened was we upscattered and we generated a power law spectrum from that, right? Even though we had a black body spectrum to start with. So we found that a power law spectrum will result from IC with a power law distribution of electrons. And so what we can actually think about is calculating a power law spectrum, if we have multiple scatterings from a non-power law distribution with a small optical depth, what ends up happening is actually we also get a power law spectrum. And this is where the complications begin, is because you can have a power law spectrum and you don't know if it's because the input spectrum was, the input distribution of electrons was a power law, or because you had multiple scatterings, even from a non-power law distribution of electrons. And so it gets complicated. And so here we can define a term called the amplification factor, which is the final energy divided by the initial energy. And that will roughly be, in the relativistic regime, roughly be equated to this, as we sort of calculated before. But we're now calling this the amplification factor. And this is sort of one portion of, right, this is the this is the average fractional energy gain per scattering, whereas the amplification ends up being the total, right? So it's the total energy change. And so we can consider a initial photon distribution here, which has energies EI, and these are going to be much less than the average electron energies, and we're going to have some intensity of that radiation at this energy. And this photon is going to go through multiple scatterings, K scatterings, and then the output energy after these K scatterings is going to be related to the input times this amplification factor to the K power. Actually, oh, sorry, I totally this wrong. The amplification factor is per scattering. Yeah, so it is exactly this term here. That's all. Right, so it's related to Y by just the number of scatterings you have, which makes more sense. Okay, sorry. Right, so then basically you have this amplification will be just this A to the K power. So if you have one scatter, you have A, two scatters, you have A times A, so A squared, three scatters, you have A times A is A to the third power, etc. Right? So hopefully that makes sense. So the medium here, if we have a small scattering optical depth, then the probability of this photon undergoing K scatterings before escape is going to be just related to tau. And so this probability is, for each scattering, will just be tau to the K. Then we can think about this intensity, the energy coming out, or the intensity of the energy at energy K is going to be proportional. So this thing here will be proportional to the input energy times tau to the K. And this will be proportional to this thing times our energy differential to some power, where this thing is now related to our amplification and our tau. So we just kind of done some manipulation here of exactly how we work this. But basically what we'll have is that we have some differential in energy here, and we have a power law coming out. And that power law is proportional to the amplification and the scattering probability. And so what does this sort of look like? If we integrate the total power coming out here, so we integrate this thing over all of the output energies, and we do this from the input energy up to some maximum here, which this maximum ends up being the amplification, the square root of the amplification times MC squared. The reason for this is that we have to maintain the assumptions from the previous equations. And so this is the assumptions break down above that. But in doing this integral, basically we have the input spectrum, the input energy, and then this integral over x to the alpha, where x again here now is just this ratio. And so what ends up happening is that you have some input here, and after zero scatter, you have basically this is x, the initial energy, right? And so you end up having, if you have zero scatters, then nothing really happens. If you have one scatter, then you multiply the fraction of photons that end up escaping is going to be proportional to tau. And so, whoops, this is our last slide. And so then the average, you have one scatter, and you'll have an energy boost of A x naught, and the amount will come out will be the incident energy times one factor of tau here, right? So, or I guess divided by one factor of tau. So you have one drop in tau. The second scatter, so there's a few photons which will end up getting a second scatter, and they will drop down by another factor of tau, and so on, and so on, and so on, and so on. And so from this initial sort of energy range here, what you end up doing is generating a spectrum which looks like this from these multiple scatterings, even though tau is relatively small. And so every scatter, even though there's a low probability of happening, if you have a large enough distribution of photons, you'll have a few that scatter, and so they will pump up this spectrum here. And so you end up with this power law, and then at some point you get to somewhere which is close to 4 kT, and then you fall off because the electron can no longer give any energy to the photon. Right? Again, this is only for a relatively small range in X here. And so then you would have a sort of larger range of X that you would have to have each of these for. But you end up with a power law distribution for each small segment of X of the energy, right? Or the change in energy. Okay. So that was a lot to take in. Hopefully it's somewhat clear. And of course, this is a very non-trivial, non-linear process, right? That's the thing to get out of this. And there are only certain regimes where we can even make realistic estimations or numerically do it. Sometimes we have to, actually do a full-blown radiated transfer to really understand exactly the interactions that come about. Right? If we don't have very specific geometries which make some of these integrals easy to do. Okay, questions about this, about anything else?
I have a question. I think that is the same direction of the last comment that you mentioned. Mm-hmm. I was wondering if in the plot in the slide 7, if maybe there is some relationship. If in some way the slope depends on the spectral index of the power law distribution or not, because here in this plot the slopes only depends on the frequency, but I can see some dependence on the spectral index.
Remember, this is only for an initial energy.
Okay.
This is again for a very small energy in the this is for a very particular gamma and a very particular energy. This is the output spectrum that will come out, right? And then we would need to integrate over gamma, and we would need to integrate over the energies. And so, you would end up with a bunch of things which looked like this, right? And then you would have some overall distribution, which would probably be some sort of power law coming out.
Okay.
Yeah. It's very hard to visualize because you get a spectrum for each distribution of energies and each distribution of electrons, right? And so then you have to sum up each. You have to go piecemeal through each of them, kind of, over a grid to kind of create the spectrum. Not trivial.
Okay.
There are some cases where you can, you know, the integrals come out and you can integrate them kind of separately or integrate them in the average sense. And we'll look at a couple of cases on Monday. Okay, anything else?
Yes, hello.
Yeah.
We must take care when we pass from K to K prime system or vice versa with the Lorentz invariant, right? For example, when you talk about emissivity, it's not just emissivity. We must use, I don't know, divided by square frequency in order to guarantee.
Right, we are divided by the energy, which is what, so when we come out here, where the hell was it? Yeah, no, it was here. Right, so in order to have it invariant, we have this extra factor here.
Mm-hmm.
Right.
Okay.
Yeah, so in fact, that's where this comes from, is that these are not, when you transform between them, they're not invariant, but this divided by this and this divided by this are. And so you can get away with it.
The same happens with the intensity, right? In the case of focus. Okay. Thank you.
Okay, anything else? The only other, so I'm going to send out a new homework later tonight. Sorry. We don't, I think Friday is a holiday, if I'm not mistaken. Let me check. And so I don't know what to do about office hours. Maybe we should have them next Monday instead. Is that right? Let me look at the, I guess it's in the AstroPH schedule. So let me see. Yeah, it's the los Glorias Nevados. Okay, so maybe you have office hours on Monday instead of Friday? Okay. Okay, well, have a good rest of your week, guys.
Okay, bye.
Bye.
Bye. See you Monday.